Right now, somewhere above your head, the sun is hanging in the sky. It looks small. Almost harmless. A little coin of light you can blot out with your thumb. But that's an illusion of distance, not a fact about size. The real answer is far stranger. If the Earth were swapped for something the size of the sun, you would not be standing on a bigger planet. You would not be standing at all. Start with the numbers, because the numbers are where this gets strange. The sun is about 1.3 million times the volume of Earth. If you hollowed it out and started dropping Earths inside, one after another, you would still be dropping them in long after you'd lost count. Your mind was never built to hold a number like that. It rounds it down to big. That's not a flaw. That's a shortcut your brain uses every single day. Cognitive scientist Stanislas Dehaene spent decades studying how the human brain handles quantity, and he found something surprising. People don't experience numbers as a straight line. They experience them logarithmically, compressed, especially once a quantity gets large. The gap between 1 and 10 feels enormous. The gap between 1 million and 1.3 million barely registers at all. So when someone tells you the sun is 1.3 million Earths, your brain quietly files that next to a lot, right beside a crowded stadium or a long line at the store. It is not built to feel the actual gap. Which means the thought experiment only starts to work once you stop imagining a number and start imagining a body. So imagine it. Earth, stretched out to the width of the sun. Same mass of rock, same oceans, same atmosphere, but spread across a sphere roughly 109 times wider than the one you're used to. What happens first isn't heat. It isn't light. It's gravity, and it happens instantly. Picture the surface before anything collapses. The horizon, which curves away from you within a few miles right now, would flatten out almost completely. A sphere that enormous would look, from ground level, nearly like a plane stretching in every direction. You could walk for days and the curve of the world would barely register underfoot. The sky above you would still be blue, for a while, air is air, but the ground beneath you would already be lying to you about what kind of place you were standing on. Gravity depends on both mass and how tightly that mass is packed. Isaac Newton laid out the relationship in 1687, and it hasn't needed correcting since. Force falls off with the square of the distance between two objects. Spread Earth's modest mass across a sun-sized sphere, and the surface gravity actually drops. You'd weigh less standing on this stretched-out Earth than you do right now. Sounds pleasant. It isn't. Because a planet held together only by its own gravity has to be dense enough to hold itself together. Stretch Earth's rock and water across a volume that large, and the material can no longer support its own structure. There isn't enough mass per cubic meter to keep it whole. The sphere wouldn't hold its shape. It would sag, crack, and slowly come apart, the way a snowball packed too loosely collapses under its own outer layer. Think about what that actually looks like from the ground, if you could somehow survive long enough to watch it. Not an explosion. Something slower and stranger. Mountains that took hundreds of millions of years to rise on the real Earth would barely register as bumps on this stretched-out one, and even those bumps would start to slump, because the rock beneath them is no longer under enough pressure to stay rigid. Oceans that once filled basins would spread thin, into shallow films draped over a surface that keeps sagging beneath them. You wouldn't feel a bigger planet under your feet. You'd feel a structure quietly losing the argument with its own gravity. You are not standing on a bigger world. You are standing on a world that is failing. Now compare that to what the sun actually is, and the twist gets sharper. The sun isn't rock spread thin. It's hydrogen and helium, compressed by its own colossal mass until the pressure at its core reaches something like 250 billion times the pressure of Earth's atmosphere. That pressure is so extreme it forces hydrogen atoms to fuse into helium, releasing the energy that becomes sunlight. Every second, the sun converts roughly 4 million tons of its own mass directly into that energy, and has been doing it for 4.5 billion years without running out. Astrophysicists studying stellar structure, building on models refined through the 20th century by researchers like Arthur Eddington, showed that a star isn't defined by its width at all. It's defined by whether it has enough mass, packed tightly enough, to ignite fusion at its center. Eddington's work in the 1920s helped explain something that had puzzled scientists for decades: how a ball of gas could stay hot enough, long enough, to keep shining. The answer wasn't size. It was pressure, and what pressure does to matter when there's enough of it. Size alone does nothing. You could stretch Earth to the sun's exact width and it would still just sit there, cold and dark, because it would never have the mass to light itself on fire. Rock and water, no matter how far you spread them, don't fuse. They just spread thinner and thinner until there's nothing holding them together at all. Meanwhile, less than 1 astronomical unit away, a sphere the same width is running a nuclear furnace so bright it lights an entire solar system from 93 million miles off. So here's the reframe. Two objects can be the same size and occupy completely different categories of existence. One is a home. One is a furnace that powers every living thing on that home. The difference was never about how wide they are. It was always about density, and mass, and what happens when you pack enough of the right material into a small enough space. That distinction matters more than it seems, because you make the same mistake the brain made with the numbers, except now you make it with people, and situations, and yourself. You look at two things that appear the same size on the outside, a competitor's success and your own, a stranger's confidence and your own hesitation, and you assume the insides must be comparable too. But size is not density. A company that looks the same size as yours from the outside might be operating on completely different fuel. A person who seems just as capable as you on paper might have spent years compressing a different kind of pressure into their skill. What looks equal at a glance is rarely equal underneath. You already knew this, somewhere. You just didn't have the image for it until now. Think about the last time you compared your own progress to someone else's. Same age, maybe. Same starting point. Same size of opportunity, at least from where you were standing. And yet one of you ended up somewhere entirely different from the other. It's tempting to call that luck, or talent, or timing, and sometimes it is. But just as often, the difference was never visible from the outside at all. It was happening at the core, under pressure you couldn't see, the same way you can't see fusion happening 93 million miles away just by looking at a bright circle in the sky. You only see the light. You never see the compression that made it. That's also why comparison feels so exhausting and so unreliable. You're measuring outer width against outer width, the only data your eyes can actually collect, while the thing that determines the outcome is buried entirely out of view. Two students can sit in the same classroom, same size desk, same length of day, and walk out with completely different amounts of change happening inside them, because density was never something a classroom could measure. There's a reason this particular thought experiment keeps circulating, keeps getting redrawn and reshared. It hands your brain something it's actually built to compare. Not a number. A body standing next to another body. Researchers who study analogical reasoning, including work associated with psychologist Dedra Gentner, have shown that humans reason far more naturally through structural comparison, this is like that, than through raw magnitude. Tell someone the sun is 1.3 million Earths and they nod and forget it by lunch. Show them Earth sagging and cracking beside the sun's furnace and something clicks that a number never could. Even the failure mode of the stretched out Earth has something to say here. It didn't collapse because it was weak. It collapsed because it tried to occupy a scale it was never built to sustain, using the same amount of material it always had. Spread yourself across a life 93 times bigger than the one you can actually hold together, more commitments, more people to please, more surface area to defend, and the same thing happens to you that happens to the rock. Not a dramatic explosion. A slow sag. Cracks in places no one else can see yet. The lesson was never spread wider. It was compress harder, on less. And that cuts both ways, because density without release is just as strange a fate as size without density. The sun's pressure doesn't build forever with nothing to show for it. It converts, every second, into light that travels outward and reaches you, warms an ocean, grows a plant, and gets read by your own eyes as you look up at a small yellow circle in the sky. Pressure that never converts into anything isn't strength. It's just weight sitting still. What made the sun matter to everything orbiting it wasn't that it held immense pressure at its core. It's that the pressure became something the rest of the system could use. And that's the real trick sitting underneath the whole exercise. Every time you're tempted to judge something by its outer size, its follower count, its market cap, its confidence, its square footage, you're doing the same thing your brain does with big numbers. You're rounding it down to a shape you can hold, instead of asking what it's actually made of, and what's happening at its core. Because here's the part that should sit with you longer than the physics does. You are not measured by how wide you spread. You are measured by what you can hold together under pressure, and whether anything inside you is dense enough to ignite. A planet the size of a star is still just a planet if nothing inside it is compressed enough to burn. And a person small enough to be overlooked can carry a pressure at their core that outshines rooms twice their size. So the next time the sun looks small enough to hide behind your thumb, remember that the illusion runs both directions. Distance can make something enormous look tiny. But size, on its own, was never the thing worth measuring in the first place. What matters is what's happening at the center, under all that weight, where the real light comes from.